Today's lesson is going to focus on the law of conservation of mass. The law of conservation of mass is a very important relationship to know in chemistry. And this was taught to you in grade 10 science. And you should recall that during a chemical reaction, matter is neither created nor destroyed. So all that means is that when we carry out a chemical reaction or a chemical change, the atoms of our compounds or our molecules or our elements are just simply rearranged from start to finish. We do not lose any and we don't gain any in the process. So in a chemical reaction, we have reactants and we have products. And the reactants are converted into products in some way. And quite literally what happens is the electrons and the chemical bonds that are holding your compounds together are broken. The electrons are rearranged. They will bond to something new and you form new products. When this happens, the total amount of reactants must equal the total amount of products created. Every atom should be accounted for before the reaction, and every atom should be accounted for after the reaction. So what does this look like? Well, sometimes it's easy to see the law of conservation of mass in play. So if we look at this first example over here, which is dealing with a physical change, we can see how if we have a glass filled with 100 grams of ice cubes and we leave that on the counter over time, and assuming no water evaporates or there's no sublimation of your gas molecules over time, because again, things can happen, we should have 100 grams of water at the end of that change or the end of that physical change. And lots of times we don't write physical changes as a reaction, but you can. Okay, so what you could do here, and it's kind of already set up for you, is you can write this reaction as H2O in the solid state reacting or changing into H2O in the liquid state. And because, losing my L there, that's supposed to be an L, because this is two different states, you can write a reaction showing the change in these molecules. If you have an actual chemical change, which our other examples are showing, again, what you notice is that at the start here of this particular reaction, you have 100 grams of something. Coal, it says coal is completely burned. So at the end of that, as long as this is a closed system, okay, so closed system means that everything is contained. And this is particularly important if you have gases involved. So at the end, if coal is being burned, there would be some gases formed, CO2 and water, probably carbon monoxide, that they're all contained in on the scale. And you notice that it should weigh 100 grams at the end of that particular reaction. Now, if we burnt a log, as we see down below, and we react it with some fire. Now, this is terrible, okay, this image, but I mean, I like it for certain reasons. I do not like it because fire is not an actual type of matter, right? Fire is energy. So I think what they refer to here is that they are burning it with oxygen. Okay, so let's denote that. Together, we have 31 kilograms of reactants going into our reaction. At the end, we still have 31 kilograms of products being made, but smoke is going to take off, okay? And again, as long as this is not a closed system, we cannot contain that smoke, okay? So we know we would see that in action. We would see it go off into the atmosphere. All that would remain are 28 kilograms of ashes, but any kind of gases, right, still have a mass and still should be accounted for. Just depending on the setup of your reaction, you may not be able to trap them. So how do we address the law of conservation of mass in chemical reactions? Well, when we carry out a chemical reaction, lots of times we just have one molecule of our reactants and one molecule of our products written down in the chemical reaction. But in actuality, sometimes you need more than one of each of those molecules either to be reacted or that will be produced. And what we do is we balance the reaction in order to satisfy the law of conservation of mass. So if we look here at this example of methane being combusted, okay, so CH4 is methane. This is natural gas that you'd see in the lab or that you would burn at home in your furnace. We know that all of these atoms have a mass associated with them. So in order to satisfy the law of conservation of mass, we have to make sure that all of those masses are equal. And if I have one carbon in my compound to start with, I have to have one carbon on the product side. If I have 4 hydrogens on my reactant side to start with, I need to have 4 hydrogens on the product side. And what's happening here is I see that I only get 2 in the formula of water, and this is why we would add a coefficient of 2 out front so that my total number of hydrogens will equal 4, just like at the start here. When I look at oxygen, oxygen is a diatomic molecule. I only have 2 oxygen atoms initially. And then I see on the product side, I get 2 formed from CO2 and I get 1 formed from water. So I have to adjust the amounts in order to get those atoms to be equal and to be balanced on both sides. When that happens, right, all of them have atomic masses associated with them. And once the numbers of atoms are all balanced, then your masses will now be equal on both sides of your reaction. So it says here to prove the law of conservation of mass with the following reactions. And what that means is, let's just show, I mean, we're not going to carry out these reactions ourselves, but we can show theoretically, right, that these reactions will be balanced in mass from reactant to product side. So here's some practice with nomenclature. I need sodium chloride. Get my pen ready here. Sodium chloride. So I need NaCl, and I'm going to react that with silver oxide. So silver oxide, silver has a charge of 1. Oxygen has a charge of 2. Do the crisscross rule, and you come up with your formula. And then we're going to make sodium oxide. Sodium has a charge of 1. Oxygen has a charge of -2. It is really, really important that you get your formulas correct. If you don't, there are times when you are not able to balance the reaction, and then you're going to have some stress and grief, okay, because it's not going to work out. Silver chloride, silver has a charge of +1, chloride has a charge of -1. We end up with AgCl. So we take a look at the reaction and we notice a couple things, and it doesn't really matter what element you start with to balance. I'll just go down the list and I'll start here with sodium. I have 1 sodium atom on the reactant side, and I have 2 of them on the product side. So I need to balance that. And one thing that you can never ever do is balance a reaction by changing the chemical formula of a compound. Okay, so because you see here that you have 2 sodiums, you cannot come over to sodium chloride and put a 2 there. Okay, you are not allowed to do that because we understand how those formulas come to be. That would imply that chlorine has a charge of 2, and we use the crisscross rule for it. Okay, so you cannot do that. What you do is if you need to balance the reaction, you will, or balance the number of atoms, you put a coefficient out front. And that coefficient applies to sodium, and it also applies to chlorine. It applies to everything in that formula. My sodiums are balanced, but I have now just adjusted the chlorines that I have 2 of them. So I come over to the reactant side, and again, I do not put a 2 after chlorine there on the product side. I'm not allowed to do that. That's altering the formula, but I can put a coefficient out front. That coefficient out front applies to everything. So it applies to silver, but it also applies to chlorine. I now have 2 silvers. I come over to the reactant side and I'm good. Okay, I have 2 silvers there. And then just double check. I have 1 oxygen and I have 1 oxygen there. Everything is balanced. We go to the next one. So we have hydrogen and oxygen creating water. So do not forget our nomenclature rules. Hydrogen and oxygen are part of the Hofbrinkel set of diatomic elements. So hydrogen is H2, oxygen is O2, and we know that water is H2O. We want to balance this. So we see that the hydrogens are already balanced, which is nice, but we notice that our oxygens are not balanced. So I need to get my oxygens to equal. And the way I'm going to do that is to put a 2 out front, which will mean that I will now have 2 oxygen atoms, and they are equal. But I just changed my hydrogens. So I now have 4 hydrogens, and so I need to put a 2 out front of hydrogen on the reactant side in order to get 4. When I look at the next one, I have aluminum fluoride. So aluminum fluoride is AlF3, okay, because we know aluminum has a charge of 3, fluorine has a charge of 1. I'm reacting it with copper 2 nitrate. So we're going to write Cu, nitrate is a polyatomic, and we're going to bring the 2 down from the charge on copper. I'm going to create aluminum nitrate. Aluminum has a charge of 3. Nitrate has a charge of 1. I need to bring the 3 down. And I'm going to create copper 2 fluoride. So fluoride is just the single element. And I end up with CuF2. So what we want to do here is balance these anions. All the metals are balanced currently, but my anions are not. And I'm going to go to my nitrates first. Okay, so what I recommend is to balance those nitrates or those polyatomic ions as a whole. And what I see here is that I have, I'm just going to change my pen color here. I see that I have 2 nitrates and then 3 nitrates on the other side. So what I want to do is I want to get those numbers in nitrates to equal. And 3 and 2 are an odd even number, which we don't love. So how do we deal with that? Well, whenever you see that you have an odd even situation like that, multiply it by the opposite value, okay, or the opposite subscript. So what do I mean by that? Well, what I mean is that if I have a 2 right here, I'm going to multiply the whole thing by 3, which is the opposite value of your nitrate ion. And if I'm dealing with this product side here of 3 nitrates, I'm going to multiply the whole thing by 2, which again is coming from the opposite nitrate subscript. So once you do that, you notice that you now have 6 nitrates on both sides. Okay, so what we do is we take the coefficient and we multiply it by copper, and then we multiply it by nitrates, which there was already 2 of them. So we have 6 nitrates there, and now we have 6 nitrates on the product side. I just changed the amounts of aluminum and copper. So let's deal with aluminum. I just now changed it. I have 2 aluminums here. I'm going to come over to the reactant side and put a coefficient of 2 down. I've now just changed my number of fluorides. 2 times 3 is 6. I come over to the product side. I need 6 fluorides, so I multiply everything by 3. I now just changed my coppers to 3, and we already had that on the other side. So everything works out. It doesn't matter often where you start to balance. The one recommendation I have is if you have a single element in your reaction, I would leave that to the very end. But generally, you can start anywhere to balance and just keep track of your coefficients. And the key thing is to make sure you start with the proper formulas.